All right, let's get into it. For decades, we've thought of satellites as these lonely pioneers, just kind of floating up there in orbit by themselves. But that whole picture is changing, and it's changing fast. We're seeing this radical shift from single, isolated units to these intelligent, cooperative swarms. So today, we're going to break down exactly how this transformation is happening, and more importantly, what it means for the future of how we all connect. And that's a really fair question, right? I mean, we've got cell towers on every corner, we've got fiber optic cables running under the ground. But here's the thing, our ground-based internet has its limits. It really struggles to reach remote areas, it can't cross oceans easily, and it's vulnerable in disaster zones. So the dream of a truly global, completely seamless connection, well, that requires us to look up, to a network that's built not on the ground, but in the skies right above us. The key here is a total shift in philosophy. The old way, it was all about building these massive, monolithic satellites. I mean, think of them like giant, self-contained mainframe computers in space. They were incredibly expensive, unbelievably complex, and if just one critical part failed, the whole multi-million-dollar mission could be toast. The new way of thinking is all about teamwork. It's about using clusters of smaller, cheaper satellites that all work together. This approach is just so much more robust, it's way easier to scale up, and honestly, it unlocks a whole new level of performance. And this is the exact problem that these new clusters are designed to fix. A single satellite, it doesn't matter how powerful it is always going to have coverage gaps. It just can't be everywhere at once. And this created a massive digital divide, leaving huge parts of our world, oceans, mountains, rural communities, completely underserved. The goal of these satellite swarms is to literally blanket the entire globe in a seamless web of connectivity. So, what exactly is a satellite cluster? Well, the absolute best way to think about it is as a single virtual satellite. Early research, like the TechSat 21 program, had this exact idea. You have a whole group of satellites, they're flying in a really tight formation, and they link up to share all their resources. They coordinate their actions so perfectly that to us down here on the ground, they behave like one massive, incredibly powerful satellite. So how do they keep themselves organized up there in orbit? Well, the most common way is something called the leader-follower model. It's pretty straightforward. You have one leader satellite that acts as the brain of the whole operation. You can think of it as the cluster manager, or maybe the conductor of an orchestra. It makes all the big picture decisions. Then you have the other follower satellites, and they're the muscle. They just get the commands from the leader and execute them. It's a really simple, elegant hierarchy that makes controlling a super complex swarm actually manageable. And all this teamwork pays off in some incredible real-world ways. First off, you get way better, more consistent coverage. Second, the signals get so much stronger. Okay, imagine you're trying to light up a dark spot with just one flashlight. Now, imagine you have 10 flashlights, all pointing at that exact same spot. That's basically cooperative beamforming. The whole cluster focuses its energy, creating a much, much stronger connection. It's also way more reliable. If one follower satellite goes down, the others can just pick up the slack. And at the end of the day, it's just a more cost-effective way to do things. Now, that sounds like the perfect solution, doesn't it? Well, as you can probably guess, getting dozens or even hundreds of satellites to act as one single unit, that introduces a whole new world of incredibly complex engineering challenges. Turns out, teamwork in space is really, really hard. And here is the first big catch. It is a huge one. For this whole thing to work, every single satellite has to be perfectly synchronized in time. If their internal clocks are off by just a tiny fraction of a second, their signals end up clashing and interfering with each other instead of working together. And the result? Recent studies show these tiny little errors can absolutely tank the network's performance by a staggering 30 to 50%. That is a massive loss of efficiency. So how precise are we talking here? Well, for perfect cooperation, you need timing accuracy on the level of an atomic clock. That's 10 to the minus 15th level. But our current capability up in orbit, it's thousands of times less precise than that. It's like trying to get a whole orchestra to play a symphony in perfect time, but some of the musicians are watching a blurry, delayed video of the conductor. It's just a massive technical hurdle we have to overcome. And it's not just about timing. It's about positioning, too. For these satellites to fly in that perfect formation, they have to know their exact location relative to each other. Now, current systems are accurate to about the meter level, which, sounds pretty good. But for the really advanced stuff, like using an entire swarm to form one giant virtual space telescope, you need micrometer precision. That's 1,000 times better. It's the difference between seeing a car from space and seeing the ant crawling on its tire. And of course, the more satellites you pack up there, the more crowded the airwaves get, and you start to get this kind of cosmic chaos. You get signals from one satellite's beam spilling over and messing with another one, kind of like crosstalk on an old phone line. You get interference between different people trying to share the same beam, and you even get whole networks like Starlink and OneWeb that could potentially interfere with each other. It's basically a massive traffic management problem, but in space. So, how in the world do we solve all these problems? Well, one of the most important pieces of the puzzle is a technology called virtual beamforming. This is where the magic of that virtual satellite concept really comes to life. The cluster uses all this sophisticated signal processing to act like one gigantic, distributed antenna. This lets it not only focus its energy, but also create multiple independent beams from the same cluster, which means it can serve many users all at once and dramatically boost the network's total capacity. So you have all these massive challenges, right? Well, engineers have a whole new toolbox to tackle them, and AI is right at the heart of it. To manage that crazy interference and capacity problem, they're using things like virtual beamforming and another technique called NOMA. For that mind-bendingly complex formation control, they're turning to something called multi-agent deep reinforcement learning. And to make sure handovers between satellites are seamless, there are flexible management systems. The real game changer, though, is enabling autonomous decisions using tools like game theory and federated learning, letting the swarm think for itself. And what's so fascinating is that this idea of intelligent, self-governing satellites isn't even new. I mean, check out this quote from research on that TechSat-21 program way back in the year 2000. They were already dreaming of this. They imagined a cluster manager with onboard intelligence that could make decisions without constantly phoning home to ground control. What was once just a theoretical dream in a research paper is now actually being coded into the silicon brains of the satellites orbiting our planet today. Yeah, artificial intelligence is really the key that unlocks the full potential of these swarms. You've got machine learning models that can actually predict where you, the user on the ground, are moving and pre-aim the satellite beams to give you a perfectly seamless connection. AI can intelligently group users into little clusters to be served by a single beam, which just maximizes efficiency. And maybe most importantly, it lets the satellites make all these complex decisions in real time, completely on their own, without waiting for commands from Earth. So, if we put this all on a timeline, here's where we stand. The basic concepts were really born back in the 2000s. Now, in the 2020s, we've seen the deployment of the very first mega constellations like Starlink. The next step, which is happening right now and into the near future, is making these constellations truly intelligent by powering them with AI. And all of this is what's paving the road for the 6G era in the 2030s, where this totally integrated space and ground network becomes the backbone of all of our global communications. And believe me, the innovation is not stopping here. Researchers are already looking at what's next. They're exploring things like quantum-inspired algorithms to solve enormous optimization problems. And they're developing something called federated learning. This is a really clever way to let different satellite clusters, even ones from competing companies, learn from each other's experiences without ever sharing their sensitive, raw data. It's like sharing the lesson you learned without having to share your entire textbook. Which brings us to a final, really fascinating thought to leave you with. For the entire history of human communication, our networks have been fundamentally tied to the Earth. But now, as these satellites are learning to think, to cooperate, and to act as a single cohesive swarm, we have to ask ourselves a new question. Is the next great global network going to be built not with fiber optic cables buried under our feet, but with intelligent light in the sky, right above our heads?